Okay, so today I will continue the proof of proposition 3.4.e. Okay. So first of all, we record what we have done up to now. We define a collection of untuples, okay, and the ith component, p sub I, is either the event E sub I or the complement. Oh, sorry. Or the complement of E sub I. Okay. So you can see that they are 2 to the nth power untuples in this set T. And we have shown that by picking up 2 different untuples and to form intersections, then they are disjoint from each other. Okay, and so we further prove that that the union of such intersections for B1, B2, and Bn from the set T, then the union becomes to be the sample space. So that with the untuples to form intersections, these intersections becomes to be a partition of the sample space. All right. And third one, okay, we consider, so we use this kind of intersection as the building blocks. Okay, and we know that they are 2 to the nth power building blocks, but maybe some of them are in empty sets. All right, so maybe some of them are empty sets, but at most we have 2 to the nth power building blocks, and we use these building blocks to build events. Okay, so that for every subset W of T, so that W will be in the power set of T, okay? Now, so we select just some of the n-tuples in the set T, okay? And to form building blocks and take the union of these building blocks, okay? All right, so that, so this is actually the collection of, so this is the collection of all possible union of B1 intersect B2 intersect intersect B sub n, okay, and where B sub I is equal to BEI or EI complement. Okay. So this is such kind of collections. All right. And so to finish the proposition, the proof of the proposition, we have to show that this collection is the smallest sigma subalgebra of F. Containing events E1, E2 up to En. Okay, so this is our purpose to show that. Okay, to achieve our goal, we first observe that since sigma subalgebra of F, which contains E1, E2 up to En, is closed under countably many complement union or intersection operations on its member. So that such a sigma subalgebra, it will contain B1 intersect B2 intersect up to intersect Bn. For all B1, B2 up to Bn in T. Because so any sigma subalgebra containing E1, E2, Bn, then it must contain each such intersections. Because Bi is obtained by either taken directly from Ei, or we take the complement of Bi, and then we take intersections. So actually, the set operations involved in here just the complement and the intersection only. We even not use the union yet. But anyway, such a sigma algebra should contain this one. So that any sigma subalgebra of F which contains E1, E2, or En must contain the collection G. All right, so the proof will be done if we show that G itself is a sigma algebra as follows. So, because any sigma subalgebra which contains E1 up to En must contain this collection. And if we can show this collection G itself is the sigma algebra, then of course G should be the smallest sigma subalgebra which contains E1, E2 up En. Any questions about the argument up to now? No, we say a sigma algebra F is that is a subcollection of F, and this subcollection of F itself is a sigma algebra.
Because it satisfies the three conditions.
Yeah, the three properties. The three properties, just like in linear algebra. We have a vector space. And what is a vector subspace? First of all, a vector subspace should be a subset of the vector space, right? And then itself is a vector space. So this is the many algebraic construction So when we say sub something, it means that it's a subset of this object. Say this is sigma algebra, right? It's a subset, but the structure of this subset has the sigma algebra structure. Okay. Other questions? Right. Now, so we have to justify this collection is a sigma algebra. So we have to check the three properties, right, of a sigma algebra. So the first part we have to say that the total event should be in any sigma algebra. Okay, but as we know from 2, right, we say that the total event, the sum space, actually is the disjoint union of all building blocks okay, from n tuples in T. Okay, right? So it's T, so that it is contained in G. Okay. So for this is quite obvious. Okay. Second, if F, okay, now, and we know okay, so if F is in G, okay, any event in G is formed by disjoint union of building blocks, right? So this is our building blocks, and we select the corresponding n tuples in a subset of T. So W here, right? W is a subset of T here. So if this one is in G, then F complement. What is the F complement? We know all the building blocks corresponding n tuples in T, right, form the sum space. Okay. Now, if F is this is built from these building blocks with corresponding n tuples in W, then you can see that the F complement actually is formed by the building blocks with corresponding n tuples from what? From F complement, which is checks equal to T and Z minus W, okay, with building blocks. Okay. For the complement, okay. So, for example, if we have, suppose n is 4, 2 to the nth power is 16. So we have 16 building blocks. Suppose each building block is non-empty, right? So we have 16 building blocks. These 16 building blocks together, right, build up the total event. All right? Now, F is built up by 3 out of 16. Suppose W has a size 3. Okay? So F is formed by 3 building blocks. Now, the F complement should be formed by the other 13 building blocks. Because we have shown these 16 building blocks are disjoint from each other, right? They are disjoint, and they form, when we take the union, we form the total events. Okay, so that the F complement actually is built up by the union of these building blocks with corresponding n-tuples is in the complement of W. Okay, so that, because it's in the complement bucket, so this is also in G. Okay, right? It's you can see that, right? This is easy things. Okay. If you played Legos before, did you? Any of you? Yeah, play Lego. You build up anything from piece by pieces, right? So they are building blocks, and different pieces of Lego are disjoint from each other, right? Because you can separate them, right? So you can think they are disjoint them. Okay, and so if you build a car, you think of this, the car is total events, but you separate them, right? You can departure into two parts. Anyway, so that then one part is built by building blocks which are different from the building block to the other parts. Okay, so just think about the Lego things, right? We play Lego, just like we play Legos here. But the building blocks we use is just these intersections only. Okay? Yeah. So you can visualize the argument here. Okay, any questions? Right, so if no questions, then the third property, if F1, F2, are in the G with F sub I equal to the disjoint union of building blocks is in Wi. Okay? Right? Because each F sub I is in G, in a collection G. And we know we form the event in G by building blocks. So we must have a Wi, which is a subset of T, right? To build the Fi. Right? So if then if we take the union, and you see right, and because Wi's, right? So why is that? Because they are building blocks, okay? And take the union means that we put all the building blocks together, right? Put all the building blocks together. So this would becomes to be, so that the building block will select from the union of So the building blocks are from untoupled, okay, in the union of W sub I. So you can think about that. You build use Lego pieces of the building block to build an object. One could be a car. F1 is a car. F2 is a bicycle, right? F3 can be an airplane. F4 something else, right? So you have a sequence of objects built by your Legos parts. But you know, if you build bicycle or build car, you may use the same wheel, right? Wheels. So they may share the same building blocks. Okay? And think about that this building block is labeled because you have to by the untoupled, right? So that they may share different, Fi may share this several untoupled together. Okay, so if you put all the objects together, right? You combine them together, then you will see all the untoupled will be from the union, right? Because just like you combine all the indexes, all the labels there. Okay, so it's that. And of course, this one is also a subset of T. No matter the union you get, right? Because each Wi is a subset of T, so the countable union is still a subset. Okay, and so from here, right, is also in G. Right. So that 1, 2, 3, property 1, property 2, property 3 required for a sigma algebra hold for our collection G. Right. So G is a sigma algebra. And then is the smallest sigma subalgebra of F, which contains E1, E2, up to En. Okay, so we complete the proof. As we have made remarks last Saturday, the building blocks, the building block, if it is non-empty, would be an atomic event. Okay, so there are atomic events in the smallest sigma algebra. Okay. If this intersection is not empty. Okay, so let me know if you have any question. Right. So now the previous two proposition is a preparation of this important proposition. This is actually our true goal in in this section. So we let E1, E2 up to En be independent events in our sigma algebra. And we let 1 to n to be the index set. Now we partition the index set into k parts. So that's right. So the partition of the index set is actually to divide the n events into k groups. Okay. For example, if n is 100, and k, and we want to divide this 100 event into 10 groups. Each group contains 10 events. So you have 10, 10, 10, 10, right? Then you have 10 groups. Each group has 10 events. This is one of the possible partition, right? But you have actually a lot of possible partitions, right? Okay, so that this is a general description how you partition or divide the n event into k groups. Okay. Now, and the k would be okay. At least you divide them into two groups, because one group is easy. It means that you did not divide them into different groups. So at least two groups. Okay, but at most n group. N group means that each group has only one event. So they treat them individually. Okay. So anyway, you see. So the purpose of partition of the index set is actually corresponding to the partition of the collection of these n events. Okay. Okay, and I also want that such that ij is not empty for all j. Okay, so the partition you can't have empty parts. Okay, so each index subset should be non-empty. Now, we let Fj be an event formed by E sub i's with I in the J's index subset. The other way formed means that the Fj is contained in the sigma subalgebra formed by the EIs and the index I is in the J's index subset. Because the events in this sigma subalgebra, the sigma subalgebra generated by EI, I is in I sub j. Okay, they are, so the event will be obtained by using countably many complement, union, or intersections on EIs for index I in the I sub j. So any questions about the meaning of F sub j? So F sub j is formed by the J's parts of the collection. Right? Then, if you form an event, you select an event from this sub-collection, sigma algebra. Okay, then you get K events. So these K events are derived from, so that the first F1 is derived from event in this collection. The second event F2 is derived from the event in the second subcollection, etc. up to the case. The case event is derived from the E sub i's, event EIs from the last collections. Now, these K events are independent. So this is the meaning of this proposition. Let me take an example before I proceed to prove. Okay. Consider five events okay, and consider F1 in, so that it is E1 union E2 complement intersect E3. Consider F2 is E4 intersect E5 complement. Suppose that. Right. So this one is in and F2 okay. So F1 is generated by E1, E2, and E3, so that F1 is in this sigma subalgebra generated by E1, E2, and E3. And the F2 is generated by E4 and E5. Okay? E4 and E5. Okay. Now, this collection is disjoint from this collection, right? You see that? This collection is from this collection. So by proposition, which are independent, I'm sorry, I forgot to say that. So we consider 5 independent events. Then by proposition 3.4.f, F1 and F2 are independent. I.e., proposition okay. So they are independent. Okay, so this is actually a very simple example here. But yeah, you can see the proposition is quite general, right? Very, very general. No matter how you partition the independent events at first, right? To form derived events, F1, F2, Fk, then this event should be independent from each other. So this proposition will help you to ease the argument, especially in the computation of events. If you originally you have some events that are independent, okay? If you have independent events at hand, and then you can, in many situations, you can use this proposition. So any questions about the statement of the proposition? Okay, so if no, then I'll proceed approve. Right, for index J, so that J would be index of different groups, right? So we now have K groups. And so J is the index of the groups. Now we let T sub J, as we built from the previous proposition. Okay. So now, because every Fj is from the sigma subalgebra generated by U1, the EI is in the J's index set. All right, so we know that Fj is the union of building blocks. Okay, so that, right, so as in the proof, of proposition 3.4.E, we have, so Fj is actually the tuples and the intersection for some Wj in the Tj for all. Okay. Okay, and so that each such smallest sigma algebra has building blocks, right? They have building blocks. So we express each F sub j as the union of these building blocks. So you may think about that, you have a k set of Lego set, right? Maybe your first birthday, you get the first Lego set. Your second birthday, get the second set, right? And at your case birthday, you get the case Lego set. And Fj is just the an object you build from the just Lego set. Okay, you can think about that. So this is just our Lego building blocks. There. And Wj, because you use just part of the Lego set only, right? Because Tj is the whole Lego piece, the collection of all whole Lego pieces in the J's Lego set. Okay, so you get, and here, and then we have the complement of J is what? Will be in Tj minus Wj of the intersection okay, yeah. Okay, so the complement corresponding to the complement of Wj in Tj. Okay, so Tj minus Wj here. So this is the complement. Now, our purpose is to show F1, F2, Fk are independent. Now, by proposition 3.4.d, right? I just state proposition 3.4.d. Okay, and this morning I just sent a proof for you, okay, for self-study. So, by this proposition, now F1, F2, up to Fk are independent if and only if A1 intersect A2 intersect up to AK, their joint probability is equal to A1 probability A2 up to probability Ak. Okay, where A sub j can be Fj or Fj complement for all j from 1 to k. Okay. Okay, So proposition 3.4.d give us an alternative set of equations to justify that k events are independent. Okay? All right, and so the AK can be Fj or Fj complement, and the joint probability of A sub j's is equal to the product of the individual probability of Aj. Okay. So now we have to show here. We have to show this one. Okay. Because our purpose is to show that F1 up to Fk are independent, but equivalently, by using the proposition 3.4.d, we just show the identities here. Whenever AK is either Fj or Fj complement. Okay? So now, with Aj equal to Fj, our Fj complement, i.e. Aj equal to the joint union of Bi, I is in Ij, in Vj of the intersection where Vj is equal to Wj if Aj is equal to Fj. And Vj will be equal to Tj minus Wj if Aj is equal to the Fj complement. Okay, so the AJs, again, we express them by using the building blocks. Okay, and this building blocks corresponding to tuples in Vj, and the Vj depends on either Aj is equal to Fj or Aj is equal to the complement of Fj. Okay, so we know that. Okay, so Vj is either equal to Wj or Tj minus Wj. Okay, so with that we have now we look at the intersection. Now we look at the intersection here. Okay, so this would be intersection, the union. Okay, just put this building blocks into here. So you can see you have intersection to the union. So by distributive law, then this becomes to the disjoint union of Bi in the index say Ij in Vj. And the union will be K here of intersection of the intersection Okay? So this is by the distributive law. Now, you see the index bi is in I sub j, but you 1 over all j from 1 to k. Okay? So that this intersection here is actually equal to the intersection of OI. Okay. So this BI. Okay. So B1. So this is actually the B1 intersect B2 intersect Bn we have before. All right. So this intersection at the end, just the union of the building block that we have, right? The basic building blocks, okay, generated by E1, E2 up to En. The all number of events, all number of events, yeah. Okay, so this is. Okay, and so now the probability A1 intersect A2. Because this is the joint union of these building blocks, so this is become the sum Bi, I in Ij, in Vj. And this is the probability of the intersection of Bi. Okay. And because E1, E2 up to En are independent, so by proposition, so this is actually the product probability of Bi. By proposition 3.4.d, by applying position 3.4.d to E1, E2 up to En. Okay. So that the intersection of Bi has joint probability, which is equal to the product of individual probability of Bi. All right, now, so we will group this product into k groups. So j from 1 to k, and okay. But this product is equal to the probability of the intersection of I in by applying proposition 3.4.d to the correction EI. I is in IJ. Because we know that if E1, E2 of EK are independent, then any sub-collection of this n event are also independent. Okay. All right. So that this is actually by applying proposition 3.4.d again. Okay. Okay. So we have sum of product, but sum of product becomes product of sum. So this is okay, and the summation Bi I in Ij in Vj of the probability okay. Okay, so this is J from 1 to K. And this is the probability of the disjoint union. Okay. But what is that? This is exactly AJ. So this is so we have done. Okay. Okay, so this is a crucial step because we express the intersection A1, A2 up to AK by the basic building blocks we created in the previous proposition generated by E1, E2 up to En. Okay. So once we have this is the most detailed structure you can have. Okay, this is the most detailed structure. Okay, right? Because we consider only E1, E2 up to En, right? So by using the n events, the smallest non-empty event you can form from E1, E2 up to En would be this kind of intersections. So this is the smallest possible event you can have. So that this is the really basic building blocks you have. Okay, so once you have that, then the following procedure is just because you have already decomposed everything to the very fundamental building blocks. So the procedure will be regrouping. Okay, you just do the regrouping step by step. Okay, so this is the regrouping process. But in the process, we apply proposition 3.4.d twice. Okay, the first time apply to the whole set of event E1 up to En. And the second time, we are applying the proposition 3.4.2 subcollection, each is subcollections. Okay, and we have k subcollections of EIs there. Okay. Right. And the other thing is just some algebraic manipulations. Okay, so we take a short break up to 2:27. Okay. Okay, so up to now, we have considered only a finite number of independent events. So the next question is that if we have an infinite number of events, how do we define independence among them? Okay. Right, so an infinite set of events, right? This infinite set can be countable or uncountable. Okay. It's called independent. If every finite subset of those events is independent. Okay, so to justify a collection of infinite number of events to be independent, then you just take only finite of them, all right? Finite number of them, and check this finite number of events are independent. Okay, and then you well know that how to justify a finite number of events to be independent. Okay, so you can, for example, you can use proposition 3.4.d, right, to justify that a finite number of events to be independent. Okay. Okay, so every finite number. So this finite subset could be a very big set. For example, you may have a trillion events there, right? Okay, you can't say I just check 2 or 3. No, you have to check and every finite number of events to be independent. Okay, and so an extension of proposition 3.4.f, because this proposition applies to a finite number of events. Okay. All right, so an extension of is as follows. All right, so let E sub I be a collection of independent events where I is an arbitrary index set. All right, so the index set I can be countable or uncountable, okay? And can be finite or countably infinite, so these are arbitrary. Now we partition this collection into different parts. So we let I sub j, j is in capital J, be a partition of the index, say, where Jx the arbitrary such that each subindex, say, ij, is not empty for all j. Right? So, because if we have an infinite number of events, suppose that we have, then we can partition this event into different groups, and the number of groups could be infinite, right? It can be infinite, or can be finite, just arbitrary. But the only requirement is that for each subindex, say I sub j, should be non-empty. Because if it's empty, it is useless, right? So we just consider non-empty index, say, there. Okay. And let f sub j be in the sigma subalgebra generated by events E sub I. The index I is in the subindex, say, I sub j. Okay. Then f sub j is an independent or just say, okay, just say it's independent, okay. So let's take an example. Consider independent events E1, E2, etc. Now we let F to be the intersection of EI for I from 2 to infinity. Okay, then probability of you can take union. Okay, you may take a union. Yeah. Then the E1 intersect F becomes to E1 times PF. by the previous extension of proposition okay. And the reason is that E1 is in the sigma algebra generated by E1 only. Okay. If it is generated by E1 only, we know that this is actually consists of four members. And F is contained in the okay. So F is in the sigma subalgebra generated by E2, E3, etc. And you can see E1, this singleton is disjoint from this collection, right? So they are in different parts. So E1 and the F must be independent of each other. So that if you consider their joint probabilities, then probability of E1, so this joint probability is equal to the product of the probability of E1 and probability of F. Okay. If you want to prove this identity, even this simple example, it becomes to be a little bit involved. But if you apply this extension here, then things becomes to be very easy. Okay, so in the future, okay, maybe in your graduate work or something else, or in any senior course involving infinite number of events, okay, infinite number of independent events, you may be able to apply this extension. But in many situations, I think proposition 3.4.f will be enough, because in many cases you only consider a finite number of independent events. But in more advanced disciplines, you may consider an infinite number of independent events there. Okay, so I think you already well prepared for the future work. Okay. Now we will consider a situation which happens quite often. Right, so this situation is here. Sometimes a random experiment okay, under consideration consists of performing a sequence of sub-experiments. For example, you may do the random experiment by tossing a coin even many times. Okay, you toss the coin 1 times, and then the second time, the third time, fourth, etc. The nth time, and maybe you can do it indefinitely. Okay, and in this kind of situation, you usually has a stopping criteria to stop to do tossing a coin. For example, you will start when you get 100 head. Suppose that, right? Usually, but you can't say when I will stop, right? It's random. So maybe you may stop at 200 tossing, up to 200, or you may stop at 1 million times, right? It depends. Even though you say just 100 heads happened, right? So that this kind of experiment, it's something called a running experiment, consistent of performing a sequence of sub-experiments, okay? All right, so now we will see how we build up a mathematical model for such kind of running experiments, which consists of performing a sequence of sub-experiments. Okay, and this sequence sub-experiment will be an infinite sequence, okay? All right, and usually sub-experiments, we usually think that the sub-experiments are independent. So we define that sub-experiments are called independent if the outcome of any group of sub-experiments have no effect on the outcomes of the other sub-experiments. All right, so formally, if E sub n is an event whose occurrence, okay, is completely determined by the outcome of the nth sub-experiment for n equal to 1, 2, etc. Right, so if En is an event, okay, and whose occurrence is completely determined by the outcome of the nth experiment, then this collection of events, E1, E2 up to En, okay, is a set of independent events. Okay, so we think that, and we have defined already the meaning of an infinite set of independent events. Okay, in the previous blackboard. Okay. it is quite often that if each sub-experiment has the same set of possible outcomes, then maybe I will say the same probabilistic structure, probabilistic structure, then the sub-experiment are often called trials. Okay. The example that we toss a coin. Okay, we toss a coin. So every time you toss a coin, each sub-experiment will have the same probabilistic structure. For example, they have the same outcome, right? Either head or tail. So there are only two possible outcomes. And the sigma algebra you select will be the power set of the set of possible outcomes. And you may select, if the coin is fair, then you may set the counting probability function, right? So the probability to have a head or to have a tail will be 1/2, for example. Okay, so in terms of the sum space, the sigma algebra, and the probability function for each sub-experiment, then they will be the same. Okay, this is to say that they have the same probabilistic structure. And so that in that situation, then we say an experiment is called a trial. Okay, it's called a trial. So whenever you read a trial, you mean that each sub experiment has the same probabilistic structure. Okay. All right, so it's quite often. So how to establish a probabilistic model, the sample space, sigma algebra, and the probability functions for a sequence of independent trials. Okay, so we will restrict ourselves to a sequence of independent trials. All right, which means that every sub-experiment has the same probabilistic structure because we call them trials. And we have independent trials. Okay. Oh, I'm sorry, I forgot to put X here. Okay, and the trials will be independent. Okay, under the meaning that if E sub n is an event whose occurrence is completely determined by the nth trial, okay, then the sequence of En becomes to be independent events. Okay, so, right, so now we will establish such a probabilistic model. There are many exercises in the textbook corresponding to a sequence of independent trials. So a trial may be tossing a coin, or maybe throwing a dice, okay, or in playing some cards. So there are a lot of trials with different natures. Okay, so we let x sub 0, f sub 0, p sub 0 be the probabilistic model of a trial, i.e. a sub-experiment okay, and here x sub 0 is the set of all possible outcomes of a trial. Okay, so x sub 0 is the sample space of a trial, and the f sub 0 is a sigma algebra, okay, of subsets of x sub 0. Okay. Okay. So when S sub 0 is a finite set, we usually set F0 to be the power set of X sub 0. Okay. When F sub 0 is the set of all real number, like the lifetime of a light bulb, or an interval in R. Okay. We usually set f sub 0 to be the Borel sigma algebra, okay, on x0, i.e. the smallest sigma algebra which contains all intervals in S sub 0. Okay. Okay, so about a trial maybe has sample space F0, which is finite. But if if the sum space of a trial is an interval of the real line, okay, then the F0, the sigma algebra, would be the smallest sigma algebra containing all intervals in S sub 0, which is called the Fourier sigma algebra on S0. All right, and P sub 0 is from F sub 0 to R. Okay, it's a probability function on the sigma algebra F sub 0. Okay, so first of all, you have to know the probabilistic model of a trial. Okay, a trial may be very simple, just like tossing a coin, right? It's very, very simple, or maybe a little bit complicated. Depends on the nature of a trial. Okay, but I believe you have the ability to establish such a probability model of a trial at this moment. All right, so this is our basic. Now we'll proceed to establish a proper probabilistic model for a sequence of independent trials. So we have to establish what is the sum space, what is the sigma algebra, a proper one, and what is the probability function. Okay? Now the sum space, okay, S of the sequence of independent trial is the set of sequences omega 1, omega 2, omega 3, etc. And such that each omega I is in the sum space of a trial S sub 0 or OI. Okay. Right, so an outcome of this random experiment is a sequence of outcomes of a trial. Okay, so it's a sequence because we do the experiment, right? To make an infinite number of trials. So the first trials. So this is the outcome of the first trial. Omega 2 is the outcome of the second trial. Omega 3 is the outcome for the third trial, etc. Okay? So this is a proper representation. All right? So this is just an outcome, okay? An outcome of our random experiments. And mathematically, this is actually equal to the Cartesian product of x0, definitely. Or sometimes this is infinity, okay? If the sample space of a trial x sub 0 has a size greater than or equal to 2, then the sample space of the sequence of independent trial is uncountable set. Okay. So you can see the complexity of this problem. Even though a trial consists of only two outcomes per possible outcome, like to toss a coin, just a very simple trial. Then the corresponding sample space of the sequence of independent trial is already an uncountable set. Okay, so that is a huge set. Okay. Okay, now the sigma algebra F. Okay, so the second element in the probabilistic model is the sigma algebra. Is the smallest sigma algebra of subset of X containing, yeah, so we require that it will containing the following events of interest. Okay. So the sigma algebra we will use would be the smallest sigma algebra, okay, containing some events which we are interested in. Okay, so what kind of event of interest? It's the event we use this name, E sub n of B. So let's see. So that would be x0. So this is n minus 1 times B. Oh, I forgot to put 0 here. So B0 here at the nth term. Okay. So which means that because you know an outcome of the sequence of independent trial is just a sequence of outcomes in a trial. Okay, so an event should be a subset of X, right? So it will consist a subset of this kind of sequences. And by definition, right, the event to describe is that at the nth term, the nth trial, specify an event bit sub 0 to occur. Okay, so this is the event, all right, occur at the nth trial, and so the first time can be any outcome up to the n-1th trial. The outcome can be arbitrary. So the meaning of arbitrary outcome would be here. So this is the Cartesian product. So the first outcome, the outcome of the first trial can be arbitrary. The outcome of the second trial can be arbitrary. the outcome of the n-1 trial can be arbitrary, but the outcome of the nth trial should be in B0, which means that B0 occurs. And the outcome at the n+1 trial can be arbitrary. The outcome at the n+2 trial can be arbitrary, and etc. They can be arbitrary. Okay, so the meaning of this set is here. Okay. All right, and so we want this kind of subset is an event of interest in our F. Okay? So where B sub 0 is in F sub 0. Okay? So it's an event. Okay? In the nth trial. All right, and so you can see that En B0 is an event. Okay, it's an event whose occurrence is completely determined by the outcome of the nth trial. Okay? So let me know if you have a question, because this is very important, because this is the fundamental events of interest. Okay, and you have to know how to express this event. Okay, and mathematically, it's actually the event is here. It's the Cartesian product, like this one. Now, if F0 is 2 to the S0, which means that each singleton omega is an atomic event in a trial. This quite often, okay, when X0 is a discrete sample space, okay. Right? So that each singleton is a trial. In this case, each singleton with omega 1, 2. Okay, so each singleton is a countable intersection of events. In above i.e. omega 1, omega 2, omega 3, etc. The singleton is the intersection and so this is the section of E sub n, omega n. So that omega is an atomic event. In the sequence of independent trial. Okay? So that's the collection C of all atomic events in F is just equal to the collection of all singletons. Okay, since X is uncountable, this collection of atomic events is also uncountable. Okay. So if you recall the proposition we have in chapter 2, all right, we only when X is the discrete sample space we can have countable collection of atomic set. Okay, so this is an example to show that if the sample space is uncountable, then the collection of all atomic events may be uncountable. Okay, of course, it's possible to select a sigma algebra such that the collection of all atomic events is countable, but that is a special case. Okay, so that we have to see the case, this example. Okay. But the very important thing is still again that these events will be the very basic events of interest we will study. And because that such an event is completely determined by the nth trial, okay, by the nth trial only, okay, and so that the events would be in the sigma algebra would be the countable complements union of intersections of these basic events. Okay, that they will be induced or derived from those basic events of interest. Okay. All right, so I will stop here, and the coming Thursday, I will specify a proper probability measure, probability function for the study of a sequence of independent trials. Okay?